Okay, up next we've got Michael from Brevis. From modularity to real-time proving.
Okay. Thank you everyone for coming to my talk. I'm Michael. I'm a founder and CEO of Brevis. And today we're going to talk about our journey of building Brevis Pico VM and our approach to kind of building this kind of high-performance ZK VM and push it to the real-time proving for Ethereum blocks. So, but before we dive into the details of the ZK VM itself, I just want to say that we are actually having this vision to build the infinite compute layer for Web3. And I know we're talking about how ZK VM can accelerate and change fundamentally how Ethereum consensus work by replacing this kind of a replicated computing method to kind of a proven, verify-based method. But I just want to say that today, you can already get the benefit of verifiable computing and specifically from ZK VM by using this kind of a new design pattern in your application level as well. Whenever you encounter something that is super complex, you don't want to run it on your smart contract, you can just let the smart contract offload this kind of a computation in this off-chain verifiable computing box. And inside of this box, which is now Brevis, it can generate a ZK proof to show that the computation is actually done correctly, and then send the result back to the blockchain so the blockchain smart contract can verify the proof easily and with extremely low latency, so you can consume the result of this very complex computation as if this happened directly on chain, right? So this pattern really actually works. That is we are today already powering numerous different applications across all the different sectors in DEXs, yield protocols, stable tokens like liquid staking, lending, different chains, perpetual DEXs, and so on and so forth. So we're actually powering this kind of a whole ecosystem. So if you are a developer and actually building something in Ethereum ecosystem, this kind of a new development pattern is something that we want to bring to the table as well, in addition to the kind of an improvement on the fundamental layer of the Ethereum execution engine. So what is inside this Brevis magic box? Well, we obviously have the Pico ZK VM, which is where I'm going to actually start today. So Pico is a very modular ZK VM with a RISC-V in ISA and a bunch of function-level precompiles. So we start to kind of building Pico around this time last year, like around the DevCon time. And so we spent about 3 months to build the first version of Pico, which is a CPU only. And when we released it at the time, we showed the state-of-art performance on the CPU proving. And the next stop is of course like a GPU acceleration on a single card, and we also achieved the state-of-art performance on that. And I'm showing this kind of a very nice sequence graph that you can show. You can see here that is showing that once we moved a lot of these kind of heavy lifting parts in the entire proving pipeline to GPU, the green thing is actually how we actually utilize the GPU, and we do very optimal kind of a coordination and scheduling between CPU and the GPU. So you can see that even on a single card, we're actually taking 100% utilization for this entire GPU proving. Therefore, we can actually achieve a very high performance, even for Ethereum blocks with 45 million guesses. So the next step for us was to basically move from a single GPU construct to multi-GPU. And there we actually did two things. One is kind of looking at this as not only just a single kind of a GPU scheduling problem, but also look at how we can slightly modify the client side of the program as well. So this is something that actually championed and pioneered by SP1 team, that they also did, they used the sub-block, and we actually followed the same kind of practice there. But first, we actually did a lot of optimization on a multi-GPU proving pipeline here that allows you to also kind of achieve extremely high performance, even with just a single machine, but running this on multiple GPUs. The key here, again, is that we actually kind of do a lot of coordination between GPU and CPU, and also the trace generation is entirely moved onto the GPU land. So now, we take the next step to essentially have this kind of a capability to run, different sub-blocks in different servers with parallel proving. And as you can see that, again, each block that right now is actually divided into 7 sub-blocks and approved on 7 GPU machines, and then aggregated finally on the last one. And this is how the kind of the entire sequence of the computation work. The thing that I want to point again is that you can see on the top there, like the entire kind of a GPU workload is very tightly arranged, and therefore like we can achieve extremely high performance when we actually do this. So today, Pico can achieve real-time proving performance for Ethereum. We released this released this in October, and we can prove 99.6% of blocks under 12 seconds and 96.8% of blocks under 10 seconds. We basically published the entire result, and it is actually replicable and reproducible. We have like an entire GitHub repo that you can actually follow step-by-step instructions to set up your server cluster and reproduce our experimental result and performance result here. And so this is actually where we are hosting our servers. And the interesting thing is that we actually this current version that we released called Pico Prism, the biggest bottleneck there is on the trace generation side. On the emulation side. So we actually did a lot of work recently on the emulation aspect of this, and basically are able to achieve this kind of additional benefit and additional acceleration in our Pico Prism v2. Unfortunately, we didn't have time to actually ship the servers so we can actually show this live in today's demo. But we're going to have the server live next week to show the performance of Pico Prism, which is going to be another sort of performance in today's ZK VM land. So how did we kind of be able to? How do we able to kind of basically achieve all this in such a short period of time? Like within like 1 year, we can build a ZK VM really from an idea to kind of a real-time proving. Well, the trick here is that we actually built this entire ZK VM in a very, very modular fashion from the very beginning. So like we actually cleanly separate the different components into RISC-V, convert, combine, and compress and embed, and finally kind of put that into the EVM verification if you need that kind of verification capability on chain. And in each of these components, we actually make it a super modular and just like a Lego. So we have a bunch of different things you can choose from, and then finally you can basically say, okay, even for fields you can choose baby bear or a koala bear. For hash functions you can use Poseidon or a Kachak or whatever. But once you kind of combine these different pieces together, you actually get the concrete ZK VM that you're using. So that's something that we did, and this really benefited the entire performance optimization process. And this is something that I want to share to you guys is that this kind of separation allows us to profile to very detailed that okay, this part is actually taking this amount of time, that part is actually taking this amount of time, so we can quickly iterate and improve the performance as we build out this entire system. So Pico is now open source. It is under one of the Pico GPU is actually under BSL, and it's actually security audited and the performance reproducible. And we're working on the formal verification for Pico as well. So now what I want to talk about is that we built this very general ZK VM that you can use to basically prove any software we want. But just like any computer systems, generality comes with a trade-off, right? So like we know that if you build very specialized circuits or very specialized system, you'll get higher performance even if you lose kind of some generality. So for Brevis as a whole, we want to operate at that point. We want to operate at the optimal point of the entire trade-off plane. So how do we do that? Well, we do that again with modularity. So we treat the ZK VM that we have as a glue, and then we are able to plug in a bunch of what we call application-level coprocessor to address some very commonly seen use cases and accelerate that further. For example, we have a coprocessor called on-chain data ZK coprocessor that allows you to generate proof of historical on-chain data such as events, states, and transactions. So the reason this kind of thing is very useful for many applications is because now you can allow your smart contract to actually see into the past and understand what is the user behavior in the past. For example, if you want to build user experience customization applications that allows you to differentiate a different user based on their past interaction with your system or with your application, you can now do that. This was something that was not possible, but only made possible with our ZK data coprocessor. So, we can clearly see the benefit of adding this kind of application-level coprocessor, because once you have this, and by the way, this is not just a special circuit like a, kind of a pre-compile. This by itself is a GPU-accelerated system as well to kind of, have a parallel proving capability to generate the individual data points. Say, okay, this guy actually swapped this, token from that token in the past, and kind of be able to put that into our ZK VM, so you can actually compute on these data points effectively. So, this is precisely the reason why I showed you in the second slide. Pico has and Brevis has so many different use cases and touching so many different spaces, because we use the ZK VM as a glue to power the infinite amount of computation in your smart contract applications. So some kind of a very simple example is that you can do dynamic fee on your exchanges now. We're launching this with PancakeSwap. We're launching this with Uniswap very soon. That allows you to essentially do that dynamic fee based on your historical trading volume. You can generate a ZK proof of your historical trading volume and get the trading fee discount. And we're also working on, we're working with one very kind of high-profile team to enable this kind of a ZK-powered perpetual swap to have a centralized exchange user experience, while it can actually settle all the matching engine match result back to the Ethereum layer 1 with Ethereum layer 1 level security and also with privacy orders. And we recently also launched this new thing with Poly Market, which is the prediction market product in Ethereum community, to allow Keynote to generate a proof of their mindshare computation algorithm, so you can actually trade mindshares without trusting Keynote as a centralized and independent platform. So there are so many kind of different applications you can do, but I don't have time to go through each of them. But my key point here is that we are actually definitely scaling up the Ethereum layer 1 with ZK VM and ZK proof. But on the application side, my prediction is that 99% of the computation for blockchain application is actually going to happen off-chain and verified hopefully by ZK proof. So with that, I'm ready to take questions.
All right, thank you, Michael. We've got a couple of questions here.
Yep.
Any plans for auto precompiles? Do they play well with your proof system?
Yeah, we're definitely looking at that and kind of playing with that for sure. So we know there are some very awesome teams that are working on that, and yeah.
Okay. Last question. You're planning to do a 2x with Pico Prism V2.
Yep.
How many security bits are you targeting right now?
Right now, 100.
And are you taking into consideration moving to 128 bits of provable security in your calculation?
Yeah, so there are several things we're looking at. Kind of on the short term, we're kind of doing further optimization on the emulation process, but we are also looking at the things like lattice. And but in a longer term, we're actually, as I mentioned in the morning, like taking a very hard and long look at the GKR-based systems. And we have already done a bunch of things on that front, and kind of going to hopefully release something soon.
Excellent. Yep. Thank you very much, Michael.
Right, thank you.